In chapter 6, we will be looking at basically all the type reactions that we will be encountering in organic chemistry. All the reactions that we will encounter can be broken down into 8 categories, and they are listed here. So what we'll do in this lecture is we will just give an overview of these reactions so that you will be able to recognize these type reactions. So the main goal here or objective here is for students to be able to look at a reaction and be able to recognize the type reaction based on these 8 reaction types. The first we look at is an acid-base reaction, then addition reactions, reduction reactions, oxidation reactions, elimination reactions, substitution. We're mostly familiar with the first 6. Here's some couple new ones. Pericyclic reactions, which I'll describe later on, and carbon-carbon coupling reactions, which we'll describe later on also. But first, let us look at acid-base reaction. We are familiar with acid-base reactions from general chemistry, but here we'll apply that type reaction to organic chemistry. But first, let's do a review on the definitions, on some definitions. We have 2 basic type definitions for acids and bases in organic chemistry. The first is a Bronsted acid. Another way of looking at a Bronsted acid, or the definition, is it's a proton donor. Notice H plus here is called a proton. So it's a species that gives up hydrogen without its electrons. The key here is it's hydrogen without its electrons. A Bronsted base is a proton acceptor. So the Bronsted base is a molecule that will accept the proton. So notice one is a proton donor, the acid, and the base is a proton acceptor. By definition, that's the Bronsted definition. Another definition is Lewis. G.N. Lewis was a chemist at Berkeley some years ago, and he coined this definition. A Lewis acid is an electron pair acceptor. Keywords: electron pair. So now you can see why I emphasized in previous lectures and in the previous chapters that whenever you draw Lewis dot structures, you include your unshared electrons on the molecule, because when reactions occur, here is where we will find electrons. A Lewis base is an electron pair donor. Electron pair donor. So look at the example below. We have BF3 and ammonia. Let's start first with ammonia. NH3, you can see here is a pair of electrons. So you can see right away it is an electron pair donor. Here's BF3. You will recall that BF3, the boron is sp2 hybridized with a vacant p orbital. Notice vacant. So it can accept a pair of electrons. So BF3 is a Lewis acid because it has a vacant orbital. And so here we have an acid-base reaction where this is a Lewis acid and a Lewis base. So you should be able to recognize those in a when a reaction is given. Another type reaction is shown here, addition. As the name implies, it's the addition of atoms or groups of atoms to a molecule, typically to the unsaturated functionality. You may recall again that we emphasize, by definition, what is the functional group. And one definition we had is that the functional group is a region of the molecule where a reaction takes place. So, here is the functional group, the alkene, an unsaturation. So that is where a reaction will take place. It's not back here, it's not over here, it is at the functional group. If we're talking about an addition reaction, we're adding Br2, for example, to the functional group, and here is the product. Bromine adds to one carbon, and the other bromine adds to the other carbon of the functional group. Here's another example of an addition reaction, adding HCl across the functional group here. So you have to recognize the functional group in the reactant in order to predict what type reaction and the products of these reactions. You can see here H and Cl can add to give two different products, because H can add to this carbon and Cl adds to this carbon to get this product. Or just imagine the reverse. H can add to this carbon to give this product, and Cl can add to this carbon to give this product over here. So again, what you need to do is to just imagine possibilities. So H and Cl adding across a double bond, and the reaction sites are basically this carbon and this carbon. So they can add one out of two ways, or two possibilities exist for the addition, and here are the two possible products. Another type reaction that we will cover here is reduction. So one definition of reduction is the supply of electrons. Keyword here, supply of electrons. And for organic chemistry, typically accompanied by hydrogen. So an example of a reducing agent is the hydride anion. Notice it's H electrons negative. That's the hydride. That's different from the proton. This is the hydride with a pair of electrons and a formal charge of -1. This will add to the positive region of a molecule. As you can expect, opposites will attract. So if we have a molecule here, such as a ketone, where this carbon is partially positive and this oxygen is partially negative, because this bond here is a polar covalent bond, this reagent here, lithium aluminum hydride, supplies H minus. So you can imagine H minus reacting right here, and here it is. A bond will break, of course, so you have O oxygen with a single bond. So this is called an alkoxide, or lithium alkoxide salt. Here's your inorganic product. Same here, if you have an imine, partially positive, partially negative, H minus is being supplied from lithium aluminum hydride. So that's your reducing agent. You can go to the stock room and buy a gram of lithium aluminum hydride. It will supply H minus, which will add right here, and here it is to give you a salt. In organic chemistry, however, we typically do not work with salts. We work with molecules that are not ionic bond but covalently bonded. So if you have your ionic salt here, lithium alkoxide, and you react it with HCl, you can see H here will react with the oxygen in an acid-base reaction to form an alcohol. So this is an alcohol functional group right here, and that's coming from your alkoxide salt. So the overall reaction, the way you will be seeing it written in organic chemistry from here on is step number 1 is the reaction of lithium aluminum hydride with a molecule, a reactant, such as a ketone. It's going to react right here to produce your salt. In a second step, make sure you add a second step because this is a 2-step reaction. In a second step, the salt is converted to the alcohol. So from here on, what you will see written is a ketone, for example, or a reactant reacting with a reagent in the first step, written by number 1. Don't forget that 1. And in a second step, there is hydrolysis to produce the covalently bonded molecule. So let us see if we can apply what we've just learned. So a typical question that you will get on your quiz and on your exam is, we want to make sure that you are thinking and can analyze a problem. So here's a question. For each of the reactions given below, provide the product and or reactant shown by the question mark. So here's a question mark. Draw that product. Give the structure of that product. You should recognize that this brew or this set of reagent in 2 steps, it's a reduction, which means it will supply H-. You should recognize this is partially positive carbon and a partially negative oxygen, so hydrogen in the form of hydride anion will add to that carbon. And in a second step, the salt will be neutralized to the alcohol. So you should be able to draw over here what is that product. Here's another example. This time we're trying to get you to think by determining what is the reactant. Notice again, organic chemistry is not just a course in terms of writing reactions and products. It is a course to get you to also think critically and analytically about problems so you can come up with good solutions. Because that is what we, as scientists, that's our job. So we have a reactant, unknown. It's given that it's a ketone. We know from this set of reagent it's a reduction because lithium aluminum hydride, and in the first step it's the reagent that reacts with this ketone, and in a second step it's the acid that gives us the alcohol. So based on the structure of this alcohol, can you determine what is the structure of the reactant? Before I tell you the answer, which is on the next slide, you can imagine that the reactant here would look pretty close to this, except the functional group would be different. Same here. You can imagine the product here would be very similar to the reactant, except the functional group here will be different in the product, of course. So let's see. So what you should have gotten is a product like this, where this is the alcohol, this hydrogen is coming from the hydride, and this proton here is coming from the water. If you're asked to predict the reactant, you know the product looks like this. The reactant will look pretty similar, except the functional group will be different because it will not have this H. Notice there's an H right here. It will not have that H because this H is supplied to this carbon from the reducing agent lithium aluminum hydride. So this would be the structure that you would draw if you're asked to give the structure of the reactant to complete this reaction. Let us look at another definition of reduction. Reduction can be described also as the addition of hydrogen molecule in the presence of a catalyst. Of course, as you know, hydrogen is it's inert, non-reactive, but in the presence of a catalyst such as platinum or palladium, hydrogen can add across a double bond, whether it is a carbon-oxygen double bond or a carbon-carbon double bond. Notice the double bond breaks and gives you a single bond, but we now have hydrogen added across the double bond. So again, if you had a question mark here and did not have a structure here, could you predict the structure given the reaction conditions? Same for the reactant. Can you predict what the reactant would have been if given the product? So try to think backwards and forwards, as we say in organic chemistry. Here's another reaction, oxidation. Let's define it first, and then we'll apply that concept. So oxidation is a removal of hydrogen and the supply of oxygen. So by definition that you learned in Gen Chem, the supply of oxygen and typically accompanied by the removal of hydrogen. As you can tell, it's the reverse of reduction. So let us look at some reagents here. Sodium dichromate in sulfuric acid. You can see lots of oxygens right here in that mixture. So that's one indication that sodium dichromate is, in fact, a strong oxidizing agent, which means that it will supply oxygen or increase oxidation state and also remove hydrogen. So if you had here a secondary alcohol of this type, notice it's a secondary alcohol which has a hydrogen on the carbon that has the alcohol group. Hope you can appreciate now why we emphasize learning the different types of alcohols, primary, secondary, and tertiary, because it will become very helpful in terms of predicting reactions based on what we're looking at now. So an oxidizing agent reacting with a secondary alcohol will form a ketone. Notice the hydrogen here is gone. Same here. KMNO4 is a strong oxidizing agent for oxygens. Here this is a primary alcohol. Here's the alcohol functionality. It has 1, 2 hydrogens on that carbon that has the OH. If that molecule is oxidized, these hydrogens are gone to produce here the carboxylic acid functional group. Notice another oxygen is added here, and we have a carboxylic acid functional group. You may be wondering where this hydrogen coming from, but water is typically added here as a solvent. Okay, our job now is to look at another reactant. This one is an aldehyde. Remember, this is an aldehyde here with an H that's bonded to this carbon. This reagent here is a oxidizing agent, so it's going to remove this oxygen, and the product that's formed is, of course, a carboxylic acid. Again, water should be here. Okay, here is another possibility. This is a tertiary alcohol. Notice a tertiary alcohol has a carbon that has an OH group, but this carbon here does not have a hydrogen. There are no hydrogens on that carbon that contain the OH group. It's a tertiary alcohol. Therefore, in the presence of a strong oxidizing agent, no reaction. Because by definition, we need that hydrogen, for oxidation to occur. Okay, let us see if we can apply what we have learned in terms of applying that concept to solving a problem. Same question. What you'll discover on my exams and on my quizzes, the wording of the questions are the same. It's just that we are applying it to different reactions. So again, same wording. Question mark, what reagent do we need? In this case, however, we have here the reactant, and we need to recognize what type reagent this is. This is an oxidizing reagent because of the presence of oxygens here. We know from definition that oxidation is the removal of hydrogen. So we can expect this molecule here to have a hydrogen, at least bonded to a functional group. We know the functional group in the product here is a ketone. So the reactant must look pretty much like this, except the functional group is different. And of course, it's given here as a hint, it's an alcohol. So you need to come up with a structure here. Here's another way of thinking of it. If given the alcohol and this reagent here, which of course you know is an oxidizing reagent because of the oxygen, what is the structure of the product? You know the product should look pretty much like this, except the functional group is different. Notice this is the line angle, so there is a hydrogen here that's not written in because that's the line angle representation of molecules. So you should be able to predict what ketone molecule or draw the structure of the ketone molecule here. And what you should get is an alcohol that looks like this for the reactant to give this ketone as a product, and a product that looks like this, a ketone, which when a alcohol of this type reacts, don't forget there's a hydrogen right here, by oxidation we get that as the product. Okay, let's look at another type reaction. This one is elimination reaction. So in elimination reaction, there is a removal of atoms or groups of atoms to form a unsaturated product. So as you can imagine here, elimination is the exact opposite of addition. So let us look at some examples. Here's an alcohol because of the OH, and in the presence of an acid and heat, so acid is a catalyst, there is a removal of water. Here is H2O. So it's being removed right across this carbon. So you can imagine here is a double bond and here is the water. So we've moved from or transformed an alcohol into an alkene by an elimination reaction in the presence of heat and a catalyst. Water is not the only molecule that can be removed from a starting material. We can remove H and Cl. The reagents are a little different though. We need a strong base and we also need heat. You'll discover that most elimination reactions require heat. So if we are taking off H and Cl across this carbon here, you can imagine it creates a double bond, an alkene, and here's our H that goes with the OH, and the Cl goes with the potassium. So that's your elimination reaction. One thing I should point out here is, and I'm sure you've thought of this, is that why is it that the elimination in the previous example took place right here? Couldn't it have taken place across this carbon here to have HOH? And the answer is yes. So we can form an alkene here which is this, and we can form an alkene here, which is, well, the opposite, an alkene here, which is this, and an alkene here, which is this. The bottom line is, elimination can occur on two sides of the OH to give water as the product. So be careful again. Think of possibilities here. So think outside the box. Is it possible to form a double bond here? And yes, it is. Similarly, it's possible to form a double bond here to get two different products. Of course, as you know, the names have to be different. Let's see if we can apply this information. So, same question again. You'll notice that the questions are the same, the wording are the same, but the reactions or what they are applied to are different. Here we have an alcohol. We have acid catalyst in the presence of heat, which is a good recipe for elimination. So we're taking off here water. Notice it can go over here because here's a hydrogen. And down here is another hydrogen. Well, there are actually two, but I'm just showing one. So if we do here, we form an alkene. Question is, can you give the structure of that alkene? Because another wording for this question is give the structure of the organic product. And we say organic because this is not organic, so most times you need not put in the water because it's considered non-organic based on our definition of organic. Thinking backwards, if given the product, the alkene, and given the reagents, which are reagents for elimination reaction, can you give the reactant? The reactant should have a structure skeleton looking like this, except the functional group here will be different in the reactant. So you may want to pause the video for a second, get your pencil and paper, and see if you can write or give this line angle structure of the reactant and the line angle structure of the product for these two reactions. What I have here is this. Of course, you may say, well, why is the double bond here? And yes, that's a possibility to put the double bond here, but you will discover that it's the same molecule because it will have the same name. And of course, here we have this as the product, and this is the elimination reagent, and we have water and KCl. That's coming from this, so we know it's elimination. So here is a good starting material here. So that's what we're trying to get students to do, is to think and apply the concepts that's being studied here. Another type reaction is substitution. As you can imagine, substitution here means just taking one molecule or one atom or groups of atoms from one molecule and substituting it for another. So here's an example. This molecule here has bromine. It reacts with another molecule that has an iodide, notice negative and positive. And since bromine is electronegative, you'd expect it to be replaced with another electronegative atom, so it becomes iodoalkane, or the iodine substitutes for the bromine, and sodium bromide, because we have sodium here, reacts with the bromine or the bromide to get sodium bromide. But the main thing here is that this is your organic molecule or the substitution product. Here's another type substitution. Here is what's that, propane, and this time we're looking at taking off one hydrogen and substituting bromine for that. We'll look at the mechanism later on in the semester. But this reaction involves bromine gas in the presence of energy, light or heat. So this brew here, or this reaction condition, gives the substitution reaction where H is being substituted for bromine, and of course the inorganic product is HBr. So let us see if we can apply that information over here for substitution. So here is KCN. So we have K plus and Cn negative. We have carbon bonding to iodine, mostly negative here because iodine is on the right of the periodic table, so you'd expect Cn to substitute for I in the product, organic product, and K and I to be the inorganic product. Look at this one. This one has the bromine and light. It has hydrogens and all of these carbons. So you'd expect one hydrogen to be substituted for one of these bromines, and the other inorganic product would be HBr. So pause the video for a while and give the organic structure here that has the same skeleton or similar skeleton, but make sure you have a substitution reaction with bromine. And over here you have the organic product that looks like this, but we're substituting KCN negative, and the inorganic product here would be Ki. I have on this slide here the answer, or the possible solution, as I prefer to make that determination. So we have KCN here, substituting for that. So here it is. Make sure you draw these molecules as clearly and precisely as possible, so that the graders can see your line angle structure. So practice drawing these molecules. Of course, the inorganic product here is Ki. Over here we have this molecule here, which has hydrogens on it. Substitution of bromine for the hydrogen gives you this organic product, and this here is HBr as the inorganic product. So again, you should be able to go backwards and forwards. So in other words, if I gave you this as the organic product and say it is a substitution reaction, can you give me the two reagents that produces that organic product? Practice that. You will see that on the quiz on Thursday. The second to last reaction type that we look at here is called pericyclic. And it's a new reaction because you didn't cover this in your Gen Chem, but it's covered more in the second semester. But what it is, it's a diene. So two enes in conjugation. And it reacts with another molecule which is just an alkene. And interestingly, these electrons move out to form a bond right here. And these electrons move out to form a bond right here. So we have a cyclic transition state, and the final product here is a cyclohexene. Notice a cyclohexene. And these reactions are extremely important, especially in natural product, because cyclic structures, especially cyclohexenes and cyclohexanes, they are found a lot in nature. So the chemist who discovered this type reaction, Diels and Alder, now called the Diels-Alder reaction, they got the Nobel Prize for this discovery because of the importance in forming six-membered rings from two reactants. Okay, let's see if we can apply this, but before that, let's do it again. So we have a diene, two enes in conjugation, reacting with a alkene, in this case ethylene, to form a six-membered ring with a double bond back here. So let's see if we can apply this reaction. So if you're asked, give the product of this pericyclic reaction, I'll tell you what type reaction it is for the time being. So here's our diene in conjugation. So here's our alkene or ethylene. So we can expect these electrons to move out, these to move in, these to move out here. So we'll form a 6-membered ring right around here. So your challenge now is to draw a 6-membered ring which has a bridge on it. So here's what I got. So here's our 6-membered ring right here, and here's the bridge. Because the reaction here is just like that, and this forms our cyclohexene. So be able to predict the products, or the organic product of a pericyclic reaction. I didn't give it here, but if given this as a product, can you predict the reactants? A little trickier, but it's something that you should be able to do. Of course, as I mentioned, next semester we have an entire chapter on pericyclic reactions. Okay, the last reaction that we look at for this chapter in this lecture is catalytic carbon-carbon coupling. Making carbon-carbon bonds is a very challenging task in organic chemistry, because as you can imagine, carbon and carbon has the same polarity. So it's very difficult to put together two atoms of the same polarity. We can put together sodium, which is on the extreme left of the periodic table, with fluorine, which is on the extreme right of the periodic table. But to put together two atoms with the same electronegativity, such as carbon, is a challenging job. So this was discovered fairly recently, and we'll study that again next semester, but I just want you guys to be able to recognize this type reaction now. A catalytic carbon-carbon coupling, catalytic because a catalyst is used, typically palladium. By the way, this reaction was discovered by a chemist called Heck, so it's known as the Heck reaction. And here's basically what it is. It's the coupling of a carbon, sp2 carbon, with another sp2 carbon. The coupling of sp2 carbons. So this carbon here bonds to this carbon to form a new bond over here, carbon-carbon bond. So once again, this carbon with the iodine, the functional group again, bonds to this carbon to form a new bond. One may ask, why wouldn't it bond to this carbon? And it does. It so happens that that will be the minor product. So if you gave that as a product, as an organic product, that's okay. That's why I give possible solutions, because I don't want you guys to think that there's one answer for all these questions that we're asking. It can, but you'll discover when we discuss that in the chapter, this is the major product, and if bonded here, it's the minor product. So let us apply this reaction type here. So here's our carbon, which has the iodine. Here is our double bond, our sp2 carbon. We have two, but we know that it tends to bond to the less crowded carbon. So we have H's here and H's here. By the way, this is the line angle structure, so we do not write the H's in. Only one H here. So it tends to bond to the carbon that's least crowded to form a new bond. So hopefully you can write the structure here. Just bond this carbon to this carbon. Here's where it becomes a little trickier, because if given this as the product, can you determine the two reactants? Let's look at the main feature here. Here is the carbon of the sp2, and here's the carbon of the sp2. So in fact, that's the bond that's being made. So you can imagine that this portion here looks like that. And this portion here looks like that, except it's a different molecule. So try and put that together and see if you can determine what are the reactants. The next slide has it, so I'll go to it, and this is it. So this is the product here for this reaction, where this carbon bonds to this carbon to produce that as the product. If given this as the product, and this carbon here bonds to this carbon, which means that this is one fragment, this is the other fragment from the sp2 carbon, and here it is. So again, make sure that your reactants and your products, they are similar in terms of carbon skeleton. In other words, you don't want to put over here this molecule down here, because the carbon skeleton over here has this feature. So again, be careful whenever you're predicting the structure of reactants and you're predicting the structure of products. They must correspond, and the only difference is what's brought about by the type reaction or the reaction conditions. I think this is the last lecture. Yes, it is. Last slide. Yes, it is. So this is all the material in chapter 6. Just an overview of the 8 type reactions we'll cover. Chapter 7 covers the first reaction in details, which is acid-base reaction. I'll try to get that posted over the weekend. So continue studying hard. We will have a quiz next Thursday, which will be over these 8 reactions here. And depending on how far we get in chapter 7, I'll let you know by email. So once again, continue studying and look out for your tutorial questions, which will be posted over the weekend. Okay? Bye.